All right, so 10.1 is properties of tangents. So this is tangents in a completely different definition of the word tangents. All of chapter 10 is now talking about circles. So we have left the polygons, we have left the triangles, we have left the quadrilaterals, and everything in this chapter, well, not everything because there's some overlap, but the focus of this chapter is all about circles. We are with a lot of vocab again, like we usually do at the beginning of a chapter, right? So a circle by definition is the set of all points in a plane that are equidistant from a given point in that plane. So if you picked a point and then you went equidistant from that point in all directions and you connected all those points, you would form a circle. The center is that point, the point that's at the middle of all those points. And the radius is the segment whose endpoints are the center and any point on the circle. The plural of radius is radii. So it's not radiuses. All right, now we've got more, right? A chord, by definition, is a segment whose endpoints are on the circle. So some sort of a segment that's passing through the circle that has endpoints on the circle itself. It doesn't mean it has to pass through the center. If it passes through the center, then it's the diameter. So the diameter is a chord, because the endpoints are on the circle, that contains the center of the circle. Sure. The secant is a line that intersects a circle in 2 points. So what's the difference between a line and a segment? A line goes on forever, so a secant will always have 2 arrows, where a chord is always going to have none. So this AB could be a chord, but line AB would be a secant. It passes on outside of the circle. Say again? No. I mean, the center, right? If I just said C, it could be the center. So a secant goes, it doesn't have to pass through the center. It's still a secant. A secant can contain the diameter. So you could have a line that passes through called AB, and it passes through the center. Line AB is the secant. Segment AB would be the diameter. I'm going to show you visuals in a minute. Okay. A tangent is a line in a plane. So again, line in a plane of a circle that intersects a circle in exactly 1 point. So secant is 2 points. Tangent is 1 point. And that point is called the point of tangency. So there's Quizlets already on this, right? Because you could start to build your slide deck. If you're a Quizlet flashcard person, all of these are vocab terms you need to know. All right, so this is what they all look like. First of all, you've got your circle, right? If this is the diameter, then it means it's passing through the center. So we could say that this center C, that's the center, okay? The diameter, if this is A and this is B, then the diameter is segment AB. A chord just has the endpoints on the circle, so it doesn't have to pass through the center. But remember, AB is still a chord. If it asks you to name that segment, though, you would classify, it's better to say it's a diameter. So you would be the more specific. If you're looking at the diameter, it is by definition, yes, it's a chord. But if it asks you to name the type of segment, it's the diameter is what you want to use. A secant is a line, so notice that it comes outside your circle with these arrows. It passes through the circle at 2 points, 1, 2, but it goes outside that circle. So that's a secant. If I had extended AB with arrows, segment AB is a diameter, but line AB is a secant. Do we understand the difference? There's not always, sometimes, never here. That's the good news. Yeah. Okay, and then the last one is a tangent. So this is a line that only intersects the circle at 1 point. It cannot cross through the circle. It just touches it at 1 point. And that point is called the point of tangency. Questions so far? What would a tangent? It would be called, which we're going to get to like later in the chapter. You'll actually learn things about a tangent segment. It would still only hit, it just wouldn't have the arrows. It would have endpoints. That would be a tangent segment. Yeah, but for right now, you don't even have to worry about it yet. We're going to get to some, don't worry, the theorems and postulates will come on that stuff. That's later. Yeah. All right, so this is all just vocab based. Point O is the center of the circle. Name each figure, so give them their name. All right, first one's OM. Yep.
I was going to ask you, what would segment ML be called?
That's still a tangent.
It's still a tangent.
Because it only hits it once. Yeah. Okay, so OM is what?
Radius.
OM is a radius. Okay, MN. Chord. All right, line MN would be what? Secant. Segment MQ. Diameter. Remember, that's a diameter and a chord, but better answer is the diameter.
So would you get marked wrong?
Yep.
But I'm not wrong.
But you're not right either. I'm telling you right now, you need to be the most specific you could be.
What if the instruction says
Now you're going to remember me saying, Matt, you need it to be the most specific it will be. All right, segment ML, we said was what? Good. So it's actually a trick question because it's the one we just talked about. It's a tangent segment.
But what about the other one?
Because it doesn't have the arrows. Now, if it has the arrows, it's a tangent.
And then M would be point.
Point M would be, good, point of tangency.
Oh God. What am I looking at? I scrolled down.
Yep. All right, so common internal versus common external tangent lines. If you draw a segment connecting the centers of the circles, okay, it is considered to be, so if I draw a segment connecting the center of the circles, this is how I test to see if that segment is internal or external. So this, we can agree, is a tangent to both of those, right?
Yeah.
Here and here. So this is called a common tangent because it's tangent to both of those circles. Now you can classify it as either common internal or common external. If I draw that little line that connects the centers of the two circles and my tangent crosses that line, it's an internal tangent. If it doesn't cross that line, it's an external tangent. So is this an internal or external common tangent? External. Do the same thing to the other side. So here I've got this is a tangent because it's tangent to both of those. It's a common tangent. Now if I were to connect the two centers of this circle, does that segment intersect it? Yes, which makes this a good common internal tangent. Okay, congruent and concentric circles. So congruent circles are circles that have congruent radii. Okay, obviously they're circles because they are both circles. But they also have to have the same size. The way they have the same size is that their radii would be the same. So both radius is in both circles would be the same. There's not like you can mark congruency on the outside of a circle. It doesn't work the way that all the other polygons work. And then a congruent circles are ones that lie in the same plane and have the same center. So they're all built equidistant from that point in the middle. It's kind of like a bullseye, okay? Those are concentric circles. The center have to be the same, but then you build your way out. Yeah.
So can circles that have the same diameter be congruent?
Yeah, because if they have the same radius, they would have the same diameter. Yes.
So the circle has to have that second outer ring or the inner ring?
For concentric circles, yeah. Okay, tangent circles, and this was really hard to draw. So Matt, before you start picking on me for how close that line is to the point. Okay, it says coplanar circles that are tangent to the same line at the same point. So this technically should be passing exactly through the middle of those. The point, they would not overlap. Okay, those are called tangent circles. These can also be tangent circles because, again, they overlap at one point. So if they are coplanar circles, that means that they are tangent, or sorry, if they're tangent circles, it means they are tangent to the same line at the same point.
So they're both.
So they could be inside or outside, doesn't matter, but they can only overlap that one point.
Oh, so they both are connected.
They're both tangent circles. It's just that one's outside, they're not overlapping, and one's inside.
So the
They're both tangent. It's just two examples of tangent circles.
so the two circles have to like meet at that specific point.
Correct. So it could be anywhere around here. It could be over here, right? These would still be tangent circles, and these two, like these two, this one would be tangent to this one, and this one would be tangent to this one because they only touch at one point. That's it. And first theorem in chapter 10, so it's called 10.1, says in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the point of tangency.
What?
So a line is a tangent to the circle if and only if the line is perpendicular to a radius of the circle at that point of tangency. So the line that's outside here, this line is my tangent. And because it's if and only if, it means in both directions, this is true, right? So it is tangent if this is a right angle, and if it's a tangent line, then that is a right angle.
Tangent line, it can't be a tangent segment.
It could be a tangent segment or a tangent line. It's still perpendicular to the radius. So where the radius hits that tangent is a right angle.
So does it? So can it be like any radius?
Any line
So if it's like
to any radius.
the radius doesn't have to be like straight. It can be like
Yeah, no, it could be like that.
oh yeah.
Yep.
That's what I was trying to-
This would still be that pink line would still be a tangent because it's still perpendicular. So there's two ways to look at it. It is tangent, so you know it's perpendicular, or it is perpendicular, so you know it's a tangent.
Tangent, so you know it's perpendicular.
Correct. Theorem 10.2 says tangent segments, so now we're talking about segments because I have to stop, from a common external point are congruent. So this is like the ice cream cone theorem, okay, because it looks kind of like ice cream cone. If you have a point outside your circle and you draw two tangent segments to the circle, they are congruent. So this would be equal to this. Any spot. So I could go here. If I drew a tangent line this way and a tangent line this way, those would be congruent.
So that means they're angles, right?
It means this, no, just the sides are congruent. Yeah, if I made it a triangle, now these angles are congruent, but we're not going to get there yet. Yeah, we'll start talking about angles in the circle soon. Yeah. Yeah, everything circle related is going to happen in this chapter. I don't know. I didn't write your book. I just teach it to you. Actually, most books have all this stuff in the first chapter of a circle. All right. Example 2 says if QR is 6, if OR is 6 and OT is 8, then RT is what? How do I know to use the Pythagorean theorem? Because that's a tangent line. If it's a tangent line, it's perpendicular. What would be RT? 10. That's a triple. 6, 8, 10. If it wasn't, I would do 6 squared plus 8 squared equals C squared, 36, 64, 100. And C is equal to the square root of 100.
Are we gonna need a calculator?
10. There's parts in the chapter you'll use a calculator, but probably for the most part, like for your quiz or your test, probably not. I'm trying to think of how far we get in 10. When we finalize your test, I'll have that answer.
For the part B, don't need a calculator, don't need a
No, but good question. So if the measure of angle OTR is 45, OTR is 45, if this is 45, and OT, wait, erase. Oh, come in. Okay, if that's 45 and OT is 4, how would I find RT? Without a calculator. What's that missing angle?
Oh,
45. What do we know about a 45, 45, 90 triangle? This would be A, this would be A, this would be A root 2. Good. Yeah, this stuff, I told you when I taught you that doesn't go away. That does not go away. Dude, this goes so much further than this chapter. Special right triangles, you will not stop seeing until you stop taking math. This is probably the hardest part of circles, is they throw a bunch of stuff into one diagram, and you got to figure it out. So this says name a line that is tangent to circle P, but not tangent to circle O. So start with P first. If this is circle P, first of all, that means that's the center. What lines are there? And again, they should not overlap on the edges. CD is a tangent, and AE is a tangent, and OB is a tangent. So which of those would not be tangent to O? OB. OB, right, is tangent to one, but it would be the secant to the other. Yes? Actually, it would be the secant and the diameter of the other. Secant goes through the circle. The line would be a secant. Well, if we called it OB, it's just that it's neither. It would have to have endpoints to be the diameter or the radius. Yeah. It can't go through it. Tangent can only touch it at one point.
And how do you know it goes through it?
This part here, you see that big part that crosses through the circle? That's how I know it crosses through the circle. All right, B, name the common external tangent to O and to P. External means if I connect these, it doesn't cross it, right? CD. CD, right? Tangent to both, but doesn't cross that line that we just made. Like CD or DC? Okay, C says name the common internal tangent to O and P. AE.
What is internal? Internal passes through, right?
Internal passes through the segments connecting the centers. AD, no, D is all the way over here.
So it's AE, right?
D's over there. So AE, do we agree that AE is tangent to both those circles? Yes. Do we also agree that it would cross this segment that connects the two centers? That makes it internal. All right, circle M and circle N are tangent at point P. So this means that this is that point of tangency. PR and SR are tangents to the circle. N and circle N has a diameter of 16. PQ equals 3. This is 3. RQ equals 12. This is 12. Diameter would tell you what? If it's all the way across, right? If that whole thing is 16. Okay, first of all, let's zoom in on MQ because that we need.
That's what I said.
Okay. What did you just say about 8? 8 would be the radius. So this would be 8. This would be 8. All the way across here would be 8. Yes?
4. It's 4. I don't understand.
Can you just relax for a moment and allow me to teach you? Thank you. N to the end of that circle would be 8. Do we agree on that?
Yes.
Because that would be a radius. Yes? Yes. So now in the smaller circle, because this is not a straight line. That's not a straight line. I can't go straight there. But in the smaller circle, this is now a diameter. Yes? Yes. So the diameter is 8. You with me? Yeah. That makes any radius in that smaller circle, which would be PM, half of that, or 4. So any radius in any direction would have been 4. Half of the big circle. Okay? So now I know PM is 4. Okay, all of this is math. Then it says MQ. So what's happening in this little shape here? What kind of triangle? How do I know that? Because if it's tangent, then it intersects the radius at a 90-degree angle. So what is MQ? 5. That's another triple. 3, 4, 5. PR, hopefully this is an easy one. 15. SR. 15, that's the ice cream cone thing, right? They both come from the same point.
Oh, yeah, okay.
NS. 8 because it's the diameter of the big triangle. NR. Oh, this is tricky.
You make a triangle.
Oh, look at you, Connor.
Oh, it's
So this would be 15. This would be 8. Then I have a right triangle. Nope. 17. That's a triple. 8, 15, 17. It's a triple. If it wasn't a triple, then you use the Pythagorean theorem. But that one's a hard one to find, right? You get the square root of 289.
How would you not get confused with all of the
I don't know. You just gotta really be careful.
like?
I would color code it, like, yeah.